in APIs. CRUD stands for Create, Read, Update, and Delete. These operations form the foundation of data management in web APIs. In FastAPI, these operations are typically implemented as different HTTP methods. The following code demonstrates simple CRUD read operations for managing items in an in-memory dictionary acting as a temporary database. In the sample code, we define a FastAPI application that allows us to create a new item, post, read an item by ID, get, update an item by ID, put, and delete an item by ID, delete. We handle errors like duplicate item creation or accessing non-existent items using HTTP exception. The storage mechanism used here is a simple Python dictionary, which helps illustrate the concept without the complication of database integration. Understanding middleware. In FastAPI, middleware is a function that runs before and after every request. It's useful for tasks like logging, authentication, or manipulating the request-response objects. Let's implement a simple middleware that tracks the processing time of each request. In this code snippet, we start by importing FastAPI and request. We then create an instance of the FastAPI application. Using the app.middleware decorator, we define our custom middleware function addProcessTimeHeader. This function records the time immediately before and after the request is processed. The difference is calculated to measure how long the request took to process. This value is added as a custom header xProcessTime in the response. Lastly, the response is returned, now including the processing time header. Creating and using middleware. Middleware is a function that works with every request before it is processed by any request handler, and also with every response before sending it back to the client. Middlewares are useful for functionalities like logging, authentication, CORS, etc. In this FastAPI application, we define a middleware using the app.middleware HP decorator. The decorated async function addProcessTimeHeader takes a request object and a callNext function. The callNext function will receive the request to pass it to the corresponding path operation. After getting the response from the callNext call, we modify the response headers, adding a custom xProcessTimeHeader. Finally, we return the modified response object, which will then be sent out to the client. Cross-origin resource sharing, CORS. Cross-origin resource sharing, CORS, is a security feature that allows or restricts resources on a web page to be requested from another domain outside the domain from which the first resource was served. In FastAPI, CORS is handled using middleware that adds the appropriate headers to the response to permit or deny requests from different origins. The above code sets up CORS in a FastAPI application by adding the CORS middleware. It permits cross-origin requests from http:/example.com while allowing all HTTP methods and headers. The allow credentials is set to true to permit credentials such as cookies to be sent with the requests. This configuration is crucial for defining which external domains can interact with your API. Designing background tasks. Background tasks in FastAPI allow you to run specific functions in the background after returning a response. This is handy for operations that should not delay the response to the client, but still need to be executed, like sending emails or processing data. In this example, writeLog is a function that writes a message to a file log.txt. It is a simple stand-in for a more time-consuming task. The endpoint /send_notification/ accepts an email as a parameter, adds the writeLog task to the background, and immediately responds to the client. The actual logging happens after the response, without making the client wait. Using background tasks in FastAPI. In a FastAPI application, background tasks allow you to run functions asynchronously after returning a response. This is useful for operations that need to happen after a request, but whose result the client doesn't need to wait for, like sending an email after a user registers. In the provided code, we import background tasks from FastAPI and define an endpoint /send_notification/. When this endpoint is called with an email, before returning a response, it adds a background task to write a log message. The writeLog function simulates a task that writes to a file, which is then called asynchronously. This means the response is returned without waiting for the writeLog function to complete, allowing the server to handle other requests immediately. Security schemes in FastAPI. FastAPI provides several security schemes out of the box, such as OAuth2 with password and hashing, bearer with JWT tokens, and API keys. Let's start with a simple example of HTTP basic authentication. This code snippet defines basic HTTP authentication for FastAPI. It utilizes FastAPI's HTTP basic dependency to protect the endpoint. When a client tries to access the /users me route, it will be prompted to provide a username and password. Our function getCurrentUsername checks the credentials. If they don't match the hard-coded admin secret, an HTTP 401 error is raised. If the credentials are correct, the username is returned. Note that in a real-world application, you would use a more secure method for credential checking and not hard-code the values. OAuth 2 with password and bearer, J. OAuth 2 with password and hashing plus bearer with JWT tokens is a common way of handling user authentication in modern web APIs. FastAPI provides tools to simplify integrating these security mechanisms into your application. The process involves accepting a username and password, verifying them, then generating a JWT token that the client can use for subsequent requests. The code defines an endpoint for generating JWT tokens when a user logs in with a username and password using FastAPI's OAuth password bearer and OAuth 2 password request form dependencies. After validating the user credentials commonly against a database, not shown here, a JWT token is created using the JWT library. This token includes an expiration time and is then returned to the user as a bearer token. The /token endpoint accepts form data and either authenticates the user or raises an HTTP exception with a 401 status code for unauthorized access. OAuth 2 with external providers. OAuth 2 is an authentication protocol that allows external providers like Google, Facebook, Twitter to confirm user identity. FastAPI supports OAuth 2 with the help of fastapi.security.oauth2.oauth2 password bearer class, which can be integrated with other OAuth 2 providers to authenticate and authorize users in your application. The provided code defines a FastAPI application with an OAuth 2 integration. We're utilizing OAuth 2 password bearer to define the authentication method, which expects a URL parameter token URL specifying where the client can acquire the token. Inside the route /users me, a dependency is created on OAuth 2's core scheme. When accessed, this endpoint will need a valid OAuth 2 token extracted from the authorization header and will then return the contents of the token. Dependency injection for security. In FastAPI, dependency injection is a powerful feature that lets you create reusable and interchangeable components. For security, this feature allows you to define security schemes such as OAuth 2 password bearer tokens or API key checks as dependencies, which can then be injected into your path operation functions. The OAuth 2 password bearer class is instantiated with the URL where the client will send the username and password to get the token. The instance OAuth 2 scheme is then used as a dependency in a path operation. When a request is received, FastAPI will check the authorization header, extract the token, and provide it to the path function where we can perform our security checks. Password hashing. In the context of web security, password hashing is the process of converting a plain text password into a fixed-size string of characters that is designed to be difficult to reverse. By storing hashed versions of passwords, you ensure that even if the data is compromised, the actual passwords are not easily retrievable. FastAPI uses passlib to handle password hashing. The provided code initializes a crypt context object with bcrypt as the hashing scheme. The hash password function takes a plain text password and returns its hashed version using the hash method of the crypt context object. The verify password function checks if a plain text password corresponds to a specific hashed password by comparing the two using the verify method. It's essential for authentication procedures in FastAPI applications. Bearer token and API key authentication. Bearer token authentication involves clients sending a token in the authorization header with the bearer keyword. This token is typically a JWT, JSON Web Token, used to identify the user. FastAPI provides a simple way to extract and verify these tokens using dependencies. In this code example, an instance of OAuth 2 password bearer is created, which expects clients to send the bearer token. The getCurrentUser function uses this dependency to obtain the token. If the token is missing or invalid, it raises a 401 unauthorized HTTP exception. The /users.me endpoint relies on getCurrentUser to retrieve the current user's information. Using scopes and permissions. In FastAPI, scopes and permissions refer to the level of access that a user has within an application. This is often used in OAuth 2, where scopes define the specific actions a client is allowed to perform, and the authentication system uses these scopes to grant or deny access to certain resources or operations. In this example, the OAuth 2 password bearer is used with a scopes dictionary to define two scopes. The getCurrentUser function is then responsible for validating if the user associated with the provided token has the necessary permissions to fulfill the required security scopes. If any required scope is missing, a 403 HTTP exception is raised, indicating insufficient permissions. Each route can use this function as a dependency to enforce scope-based security. The read items endpoint signifies that it requires a user with the appropriate token and scopes to access it. Writing test cases for FastAPI. In FastAPI, writing test cases is crucial for ensuring your application behaves correctly. You can use the TestClient provided by the Starlet framework, which FastAPI is built upon. This client allows you to send HTTP requests to your FastAPI application and assert responses for testing. You will typically use the Pytest framework for organizing your tests and making assertions. In this code snippet, we first import TestClient from FastAPI's testing module and the application app from the FastAPI application module, presumed to be my app. We then instantiate the TestClient with our app. The test function testReadMain is a simple example where we send a GET request to the root endpoint / of our FastAPI application. We assert that the status code of the response is 200, indicating a successful response. And we also assert that the JSON content returned matches the expected response, which is message, hello world. This test ensures that the main route returns the correct status code and response content. Pytest for testing FastAPI apps. Pytest is a powerful testing framework for Python. When used with FastAPI, Pytest aids in creating tests for API endpoints to ensure that they behave as expected. In the FastAPI context, tests commonly involve sending HTTP requests to the API endpoints and asserting the responses. Here's how you can set up a basic test using Pytest. The code snippet shows the setup for a basic test. A TestClient instance is created from my app, which includes the FastAPI app object. The test function testReadMain performs a GET request to the root endpoint / using the TestClient. After making the request, the test asserts that the response's status code is 200, HTTP OK, and that the response JSON matches the expected output. Pytest will collect functions prefixed with test within the test module and run them as tests. TestClient for API route testing. The TestClient provided by FastAPI works together with Pytest to simulate requests to your web application, offering a simple way to validate the behavior of API endpoints during testing. Instead of sending real HTTP requests, it uses the Starlet TestClient, which makes it fast and does not require running the server. In this code block, we import TestClient from FastAPI.TestClient and the application instance, app. We create a TestClient instance by passing in our FastAPI application. Then, we define a test function testReadMain that uses the client to simulate a GET request to the root endpoint. The assert statements are used to verify that the response has a status code of 200 OK and that the response JSON matches the expected value. Coverage reports. Coverage reports are a tool used to measure the extent to which the source code of a program is executed when a particular test suite runs. This helps in identifying parts of the codebase that are not covered by any test cases, indicating potential areas for writing additional tests to improve code reliability. First, we install the coverage package using pip, which is necessary to generate coverage reports. After installation, we run the test suite with coverage run, specifying the test module, in this case Pytest. Once all tests have been executed, we use coverage report to get a simple report on the command line. The -m option shows the missed lines. Additionally, coverage HTML generates an HTML report, providing a more visual and detailed view of the coverage, with highlighted lines indicating covered and uncovered code segments. Testing asynchronous code. In FastAPI, You might deal with asynchronous code, which requires special constructs to test. The core TestClient, designed to work with FastAPI, uses a context manager to ensure that asynchronous code is run in the event loop. This allows us to call async routes and get their responses for testing. The code defines a simple test function to test the route of a FastAPI application. We create a TestClient instance, passing the FastAPI app object to it, which can be used to make requests to the application. The client.get/line simulates a GET request to the root endpoint. After the request, we check the status code is 200, indicating success, and that the JSON response matches what we expect. The TestClient handles the async nature of our app, allowing us to write tests as if they were synchronous code. Mocking dependencies and external services. When testing FastAPI applications, you often want to avoid making calls to external services or databases, as such interactions can cause your tests to be slow, flaky, and difficult to isolate. To address this, you can mock these external dependencies using tools like unittest.mock from the Python standard library. This allows you to simulate responses from the external service and ensure your app behaves as expected without the need for the actual service during testing. In this code snippet, we're using unittest.mock.mock to create a mock object that will override the getDB dependency used by FastAPI endpoints to access a database. Instead of connecting to the actual database, this mock will return a testing session local object, which can be a predefined database session configured for testing purposes, with a pre-populated test database or an in-memory SQLite database, ensuring that tests do not affect the real database. Automatic API documentation with Swagger OpenAPI. FastAPI automatically generates interactive API documentation using Swagger UI. This happens by leveraging the OpenAPI standard, allowing for easy visualization and interaction with the API's endpoints. Swagger UI provides a web-based interface where users can read the documentation, submit requests, and inspect responses without writing any code. In this code snippet, a FastAPI instance is created and a single GET endpoint is defined. The endpoint/items item ID takes an item ID as a path parameter and an optional query parameter Q. When you run this FastAPI app, Swagger UI will be automatically available at stocks. No additional setup is required. By going to stocks in your browser, you can see the interactive documentation, where you can not only see the API specification, but also send requests to the defined endpoint and see the responses in real time. Redoc for API documentation. Redoc is an alternative API documentation tool that can be used with FastAPI to present your API schema in a clean, interactive format. It's known for its 3-panel design and clarity, providing end users with a great developer experience. It automatically generates reference documentation from your OpenAPI specification, OAS. FastAPI can be configured to use Redoc right alongside its default Swagger UI documentation. In the provided code snippet, we define a FastAPI app and create a simple route that responds to GET requests at /items/item ID. The placeholder item ID is a path parameter that the function readItem expects to receive as an integer. With this setup, if you run the FastAPI server and go to /redoc in your web browser, you will see the Redoc page rendering the auto-generated documentation, which will include the newly defined /items/item ID, endpoint and its documentation. Customizing API documentation. FastAPI provides a built-in solution for auto-generating API documentation using tools such as Swagger UI and Redoc. By default, these are accessible at /docs and /redoc, respectively. However, you might want to customize the documentation to add more information, change its appearance, or add extra security. The provided code demonstrates how to set up a custom route for Swagger UI. By using the getSwaggerUI HTML function, you can point to custom JavaScript and CSS to alter the appearance of Swagger UI. The OpenAPI URL parameter points to the OpenAPI schema generated by FastAPI, title sets the page title, and Swagger JS URL and Swagger CSS Fest URL are used to specify the custom Swagger UI files. The include in schema equals false argument excludes this endpoint from the generated schema to avoid it showing up in the documentation itself. API versioning strategies. API versioning allows developers to iterate on APIs without breaking contracts with existing clients. There are several strategies for versioning, we'll cover path parameter versioning and query parameter versioning. In the provided code, we have two different API routers, v1 router and v2 router, each representing a distinct version of the API endpoints. We define two versions of the read items endpoint. The v1 version returns a predetermined list of items and a version marker v1, whereas the v2 version returns a different list with a different version marker v2. By including these routers with prefixes v1 and /v2 in the main FastAPI app, we create distinct namespaces that reflect the version of the API, which can be accessed via paths /v1 items and /v2 items. This is a straightforward example of path parameter versioning, allowing clients to choose which API version to use based on the URL path. Maintaining multiple API versions with FastAPI. Versioning APIs is a crucial aspect of API development, as it allows for updates and improvements without breaking existing client integrations. When using FastAPI, different API versions can be maintained by organizing the endpoints into separate modules or by using different path prefixes. Here's an example using path prefixes. The code snippet demonstrates how to set up two versions of an API using FastAPI. Two router objects, v1 router and v2 router, are created to represent each version. We define version-specific endpoints under each router object. Then we include these routers in the main FastAPI application using the includeRouter method with a specified prefix that differentiates the API versions, e.g. /v1 for version 1 and v2 for version 2. This allows clients to access different versions of the API by changing the URL path. Containerization with Docker. Containerization with Docker involves packaging an application with all its dependencies and configurations into a Docker container. This container can then be easily deployed and run on any system with Docker installed, ensuring consistency and simplifying the deployment process. Below, we create a Docker file to containerize a FastAPI application. This Docker file uses a base Python 3.9 image from Docker Hub. It installs FastAPI and Unicorn, an ASGI server, copies the application source code from the local directory ./app to the containers/app directory, and finally specifies the command to run the application using Unicorn, binding it to port 80 and accessible from outside the container. Using Docker Compose for local development. Docker Compose is a tool for defining and running multi-container Docker applications. For local development, it allows you to configure your application's services, networks, and volumes in a single Docker Compose.yml file, bringing up or tearing down your entire stack with simple commands. In this Docker Compose.yml snippet, we define a service called Web that builds our FastAPI application from the Docker file located in the .app directory. The service maps the host's port 8000 to the container's port 8000, enabling us to access the app at localhost 8000. The Volumes section mounts the local /app directory to the /app directory inside the container, which allows for automatic code reloading when files change. The command overrides the default command in the Docker file with Unicorn, running the FastAPI application and enabling hot reloading with the mash reload flag. Deployment strategies: Heroku, AWS, GCP, Azure. Deploying a FastAPI application to Heroku requires creating a proc file, specifying required packages in requirements.txt, and setting up Heroku CLI. Heroku will automatically detect the app as a Python application and use the specified command in the proc file to run your application. The proc file tells Heroku to start a web process by running the given command. Unicorn main app indicates that Unicorn should use the application instance named app in the main module. Heroku dynamically assigns the port via an environment variable port, which is referenced in the command. HTTPS and TLS. When deploying a FastAPI application, it's essential to secure the communication between the client and the server using HTTPS, Hypertext Transfer Protocol Secure, which utilizes TLS, Transport Layer Security, to encrypt the data in transit. To enable HTTPS, you typically need to obtain an SSL TLS certificate and configure your web server to use this certificate. In the code snippet above, we're deploying a FastAPI application with HTTPS by running the Unicorn server with SSL TLS support. The SSL key file argument points to a private key file, and SSL cert file points to a certificate file that you've obtained from a certificate authority. This allows the server to establish TLS connections, ensuring encrypted communication. Note that this approach is for demonstration, and there are better ways to handle production-grade HTTPS configurations, such as using a reverse proxy with HTTPS. Domain configuration. When you're ready to deploy your FastAPI application to a production environment, you'll need to configure a domain name that routes to your API. This often involves setting DNS records to point the domain to your server's IP address. Domain configuration does not involve actual FastAPI code, but rather the setup on the domain registrar's side and your DNS provider. You'll typically set an A record that points your domain to the server's IP address where your FastAPI app is running. If you're using a cloud provider like AWS, GCP, or Azure, they may provide a domain name service that allows you to configure DNS settings. Additionally, for HTTPS, a CNAME record might be used to verify domain ownership and issue an SSL certificate through services like Let's Encrypt. Server setup: Nginx, Uvicorn, Gunicorn. Setting up a production server for a FastAPI app involves using Uvicorn as the ASJ server, with Gunicorn as the process manager to handle multiple processes, and Nginx as a reverse proxy to serve static files and manage HTTP requests. The Gunicorn command starts multiple processes of Uvicorn, leveraging Uvicorn Worker as the worker class for running the ASGI application. In the Nginx configuration, the server block defines the behavior for incoming HTTP requests. The proxy pass directive forwards requests to the FastAPI app running on Uvicorn. The location's static block serves static files directly via Nginx, which is more efficient than serving them through the FastAPI application. Each directive contributes to a robust, scalable server setup for deploying FastAPI applications. Performance optimization best practices. Pydantic models help in validating data, which helps in preventing errors and ensuring data consistency, indirectly improving performance. However, excessive use of models for simple operations can introduce a slight delay. Pydantic models are FastAPI's default for data validation and serialization. While they add useful validation, consider when it's appropriate to use them. For operations that don't require validation, or when working with large amounts of data, it may be more efficient to bypass Pydantic models to avoid the validation overhead. Async and await, managing asynchronous operations. In the context of FastAPI, asynchronous operations allow for concurrent processing of tasks, which can improve the performance of I/O-bound applications. The async keyword marks a function as an asynchronous coroutine, and await is used to pause the coroutine until an asynchronous operation completes. This allows other tasks to run in the meantime, which can lead to more efficient use of server resources. In this code, we define an endpoint/data using FastAPI that is handled by an asynchronous function getData. Inside this function, we await another asynchronous function fetchData that simulates fetching data from a database. By using await, we tell Python to wait for fetch-data to finish and return control to the event loop to handle other requests or tasks. Once fetch-data completes, its return value is sent back as the HTTP response. This demonstrates how FastAPI enables asynchronous I/O operations to enhance the scalability of web applications. Concurrency and workers. In web applications, concurrency refers to the ability to handle multiple requests at the same time. Workers are processes or threads that run the application. FastAPI, being an async framework, allows for high concurrency, but it also depends on the underlying server and how you configure it. The code snippet is for running a FastAPI application with Uvicorn, an ASGI server. It specifies that the server should be initialized with 4 worker processes. Using multiple workers allows the application to handle more concurrent requests by leveraging multiple CPU cores. It's essential for scaling applications to accommodate higher traffic. However, each worker is a separate process with its own memory space, so if they need to share information, it requires a shared data store or message passing mechanism. Scaling FastAPI applications horizontally. Horizontal scaling, also known as scaling out, involves adding more instances of an application across different machines or processes to handle more load. When scaling a FastAPI application horizontally, the application state should be stored outside the application instances to ensure consistency across instances. In this code, we use uvicorn with multiple worker processes to scale a FastAPI application. The command starts uvicorn with 4 worker processes serving the FastAPI application, allowing it to handle more requests in parallel. It binds the server to all network interfaces, 0.000, and sets the port to 8000. Each worker is a separate process, able to handle requests independently, increasing the application's ability to serve multiple requests concurrently. Deploying with orchestration tools, Kubernetes. Deploying a FastAPI application using Kubernetes involves creating container images of your app, defining Kubernetes manifest files, and using kubectl or other deployment tools to manage the application. Kubernetes provides scalability, load balancing, and self-healing by managing clusters of containers. The code provided includes 2 Kubernetes manifest files, a deployment and a service. The deployment describes a desired state for the application, informing Kubernetes to run 3 replicas of the FastAPI container. The service exposes the app to the network, using a load balancer to distribute traffic to the pods running the FastAPI application. Kubernetes ensures high availability and load distribution among the instances of the app. Application design principles. Separation of concerns is a design principle for separating a computer program into distinct sections, such that each section addresses a different concern. In the provided code snippet, we've separated concerns into 3 distinct areas: authentication, verify token, business logic, get items service, and the presentation layer, read items route. This allows for clearer organization, easier maintenance, and enhances the ability to test components in isolation. API design best practices. API versioning is important for maintaining backwards compatibility and allowing clients to adapt to new changes gradually. A common approach is to include the API version in the URL path. The code defines 2 endpoints, each pertaining to a different version of the API. The first endpoint /AAV1 item/ returns a simple list of items, while the second endpoint APA2 returns a more detailed list of items with ID and name. This approach allows clients using the older API version to continue functioning without immediate changes. Project structure and organization. A well-organized project structure is crucial for maintainability and scalability. In FastAPI, this typically means separating concerns into distinct modules and directories, adhering to the principle of single responsibility. Commonly, a FastAPI project may include separate folders for models, schemas, routes, endpoints, services, and dependencies. In this structure, main.py is the entry point of the application where FastAPI is initialized and routes are included. Dependencies.py would contain dependency injection mechanisms or utility functions. The routes directory houses the individual route files, which define the endpoints. Models includes the database models. Schemas defines Pydantic models for request and response data validation. Services contains business logic, and the tests/ directory is reserved for test cases. The requirements.txt file lists the Python package dependencies. Dependency management. In FastAPI, dependency injection is a powerful feature that allows you to create reusable components that can be injected into path operation functions or other dependencies. Dependencies can encapsulate shared logic such as database sessions, authentication, and more, keeping your codebase dry, don't repeat yourself, and easy to maintain. In this code snippet, the common parameters function is defined as a dependency. It takes query parameters and returns a dictionary. The depends is used in the path operation function read items to indicate that it requires the common parameters dependency. FastAPI will call the common parameters function and pass its return value to read items as the commons parameter. The commons dictionary can now be used inside read items for handling the request, thus separating concern and enhancing code reusability. Logging and monitoring. Logging in FastAPI applications is critical for tracking events that occur while it's running, especially in production. Python's built-in logging module is commonly used for this purpose. Here's how to configure it. In the provided code snippet, we import Python's logging module and set the basic configuration with basic config, specifying the logging level as info. In an endpoint, we record an info message using logging.info. When the /root is accessed, it logs processing default request. This is the simplest form of logging, but it's essential for monitoring application behavior and debugging. Configurations and environments. In FastAPI and any substantial application, handling different configurations for various environments, development, testing, production, etc., is crucial for separating concerns and preventing sensitive information from leaking into the wrong places. Here, we'll look at a strategy to manage different settings using environment variables and Python's built-in OS module. In the code, a settings class is used to encapsulate configuration variables. Environment variables are accessed using os.getEnv, which allows you to provide a default value in case the environment variable is not set. This approach keeps your configurations dynamic and secure. The settings are used across the FastAPI application without hard-coding any sensitive information. The /info endpoint demonstrates how you might expose these settings, although in a real application, you would likely keep this information internal. WebSocket support. FastAPI provides built-in support for WebSocket, a protocol that enables two-way interactive communication sessions between the user's browser and a server. WebSocket can be used to send messages to a server and receive event-driven responses without having to poll the server for a reply. This is especially useful for real-time web applications. In this FastAPI application, we define a WebSocket endpoint at the path /dus. When a client connects to this endpoint, we first accept the WebSocket connection. Then, we enter an infinite loop where we await messages from the client. When a message is received, we extract the text and send back a response to the client, containing the received message. This simple echo server demonstrates how to handle incoming WebSocket messages and how to send responses back to the client. GraphQL with FastAPI. FastAPI has built-in support for GraphQL, an alternative to REST APIs that allows clients to request only the data they need. For integrating GraphQL, FastAPI relies on the Graphene library. Below is an example demonstrating how to set up a basic GraphQL endpoint in a FastAPI application using the Graphene library. In this code snippet, a basic FastAPI app is configured to serve a GraphQL API. First, the necessary imports are made from FastAPI, starlet.graphql, and Graphene. A query class is defined inheriting from graphene.objectType with a single field hello, which takes an optional argument name. The resolver method, resolveHello, returns a greeting string using the provided name. The FastAPI app instance is created, and the GraphQL API is made available at the root path by adding a route with GraphQL app, which takes a graphene.schema with the defined query class. Server-sent events, SSE. Server-sent events, SSE, is a technology that enables servers to send updates to clients over a single long-lived HTTP connection. In FastAPI, you can use SSE to push real-time updates from the server to the client without requiring the client to continuously poll for changes. In this code example, we import FastAPI and response from FastAPI and event source response from SSE starlet.sse to handle SSE. We define an endpoint /events using the async function getEvents. Inside, we define an async generator function, eventGenerator, that yields a dictionary representing an SSE message every second. Event source response takes this generator and manages sending the events to the client, properly formatting them, and keeping the connection open.